terms of why you want to go to grad school is that it's not that hard. Y'all think, oh, grad school's for geniuses. It helps to have some aptitude, but reality is you just have to be willing to do it. That's about 90% of grad school is your willingness to do it, to show to your advisor and to a future employer that you're willing to do the extra mile. And also, you go through grad school to solve a problem that has not been solved. Right now, in honesty, all these problems I give you, they've been done before. But you're seeing them for the first time, so it's relevant. All right, but then after this, I've gone as far with you as I can. The next thing in your education is to take a problem. Did I not say that right? Yeah, water. So the next step in your education is to answer a problem that I don't know the answer for, right? And what that does is that changes you. It changes your way of thinking. All right, now here's another example. Take that entropy deal, the KLNW. There's only certain select problems where I can determine. Remember how we did a gas goes from the right-hand side to the left, left-hand side to the right-hand side, and I had a description of the microstates. There's only a certain number of select problems that are real that I can do that calculation for. So why bother? The answer is because it changes the way you think. It changes the way you think in a way that's more correct than the way you used to. That's what grad school does. Then you go out and you be more productive citizens because you can think right. And you did it by solving a problem for which we didn't know if there was an answer. Is that scary? Yeah, a little bit. But life favors the brave, right? No guts, no glory. So what happens is, because I've done this unfortunately twice, I've had students work for an entire year on a project with no answer. What happens is you stop, all right? And then you find a different problem. That happens, it's unfortunate, but again, no guts, no glory. What'll happen is after you graduate, in about 5 years, and you're paid about $25,000, 5 years of this, so I mean, it's not great, but it's the thing is that when you get out, you make about 80, right? You're gonna roughly triple your income. Also, now when I was your age, and after I had graduated, I was bored. I was sick of school, I just wanted out, I wanted to just do my mindless tasks, go home and just watch The Simpsons, all right? And I did. The problem was I tend to take my work home with me. And everyone I worked with was nice, but I'm not the boss. And that sucked because I saw what people were doing and I'm like, this is freaking stupid. But there's a ceiling, right? And I was below it, and I'm always gonna be below it because I don't have a PhD. The place was run by PhDs, the peons were me, everyone without one. And that sucked because I kind of belonged in that bracket, but I didn't have me a PhD, now did I? So I went to grad school. And everything was paid for because I was taken by a guy who had the money for me, and if I don't, I don't take a person, so you're insulated. Didn't make a lot of money, but I didn't starve either. And then when I got out, now I make $90,000 a year. And by the way, remember I told you this, I grew up in a housing project in Alabama. All right, I bet a lot of you lived in government assistance too. So, and you can get out of that and become a $90,000 a year millionaire like me. All I have to do is save 11 years, right? 12 years. And look, my life is really comfortable. Whoever said money doesn't buy you happiness was born rich. Seriously, because worrying about money sucks. If you're worried about money and paying your bills, how can you be happy? You can, but it's a lot harder. With me, I worry about what kind of souffle will I have tonight? Not, gee, I wonder if I'll have hot water tomorrow. Which life is better? Which one's happier? I contend the one with souffle in it. I can afford another kitty. You can have no kitties. So anyway, grad school is a really good idea. You'll make more money, you get to be the boss, you have an interesting job, and I can just tell you, I know it doesn't mean a lot to you now, but in life, if you don't go into management at some point, as much as it sounds like it sucks, if you don't go into management, you're kind of failing, right? You need to become a manager at some point because that's when you're in charge, and you should be in charge because you're older and you have more life experience, and if you're not sharing that with other people, what are you doing? Plus, you get paid. So, any other questions about grad school? So go to grad school. If you can get in, go to grad school.
If you accept us.
But stop there. There are 230 PhD, chemistry PhD granting institutions in this country. Actually, I think there's more. There's one for everyone, for certain. And no matter what, it's a good idea. And so now some of you folks looked out, most of you, I'd say at least 1/3 of you were not born in this country, and about the other 1/3 were born to parents born outside this country. I'm second generation, by the way. My grandparents were immigrants, so that's why I work hard. If I was like the rest of them, I wouldn't. And sometimes you folks, I hear complaints like, well, my TA is new to this country and I have trouble understanding them. The reason they're here getting their PhD and eventually becoming your supervisor is because you won't. To be perfectly blunt, if you don't go to grad school and become, you TA, all right, whatever, it's how you pay the bills. Notice that this person's going to be your boss. And they became the boss by doing it because you didn't. So Americans don't go to grad school. We have to take in foreigners into our grad school because Americans don't apply. You just take your regular job and go home and watch The Simpsons. And you have no kitties. So seriously though, it's really screwed up that America has so many graduate level positions and we can't fill them. We have to bring in people from the outside or the positions go unfilled. And we can't live with that. We can't. Or our economy crumbles. Because PhDs are innovators. They're innovators because they solve problems that we didn't know had solutions, and that's why they're going to be your boss. So, any other questions? Go to grad school. Don't become a professor, just go to grad school, all right? There's enough professors anyway. Okay, we said, sorry, I'm rambling my mouth too much. I actually only have 3 pages, so 45 minutes I can do 3 pages. So, all right, sorry to blah, blah, blah. Let me remind you, let's do more adiabatic, reversible, derivations. Adiabatic reversible derivations. These are the hard ones, but remember that adiabatic reversible machines are perfect machines. That's like Carnot machines, right? And the first example you had was on a test, which was a little, I hope you don't think that was unfair. What was really being tested on the test was whether you remembered to juggle, that you can juggle these partials around. That's what I really wanted to know, right, over P, right, CV minus sign. I just wanted I wanted to see whether you knew that. So this was a curveball type question. What's held constant? What's held constant is S because this is an adiabatic reversible equation. So I've already decided that S is constant. Okay, this was blindingly easy. Now on your homework, let's make this relevant to the homework. I'm asking another adiabatic reversible derivation of the GDP, a constant S. Okay, that's your homework. Let me do an example that's blindingly similar. All right, let me change the the G to A. And if I'm going to go from G to A, I'm going to take the P to a V. Let's do that at constant S. Okay, now obviously your homework answer will be similar, except take all the V's and turn them into P's, right? So, not to make it a giveaway, but regardless. Okay, now, as in all things, I see the change in A, so I'm going to write the change in A. So SDT, because T is the natural variable. Oh, I remember that A is the one with all negatives, so I know I've done it right. Just a little factoid I remember. And now I divide by dV, a constant S. Okay, and this guy, this dt dv, I have it right here. Now, I'm writing this the way I wrote it because this is what I did in that second hour last Friday. What I'm testing here is, do you remember to flip it? So this is minus S times P. I have to flip it over CV, minus plus, and then I've got minus P. Okay, and then let me factor this. The answer on your homework will be very similar. Okay, there you go. I'm just factoring it. I'm factoring it for a good reason, because the next question is, okay, that's like question 1 was question 2. Question 2 is, does A increase with V at constant S? Given that entropies, as I said in the last hour, entropies tend to be, look at the table of entropies, and again, it's for standard state temperature and pressure. But let's just say that I'm asking this question at standard state temperature and pressure. How is A changed with V? That's just for gases, and we're still in gas land when I'm doing these derivations. S's tend to be 100 to 300. 100 for like helium, 300 for like butane. CVs are CVs. You know what those are. Those are 10 to 20. Okay, so this is bigger than 1. A number bigger than 1 minus 1 is positive, positive, okay, net positive. So there you go. You know that I asked, does A go up with increasing V at constant S? The answer is yes, that's how you know. Again, notice that the complication of having absolute S, it's good that I know what the absolute S is. This is why we bothered to determine the absolute S of everything rather than relative S. We could have, but it was too important. S on its own keeps showing up in so much stuff. I wanted to know what SO is, not relative S. Okay, so, okay, here's another neat thing. Let me, what do I want to do here? Okay, what are the, let's look at this one here. What are the units? Oh, but there's so much stuff. There's only one unit.
Joules.
Right here.
Pressure.
Nope. Pressure, right, remember. I'm going to start asking questions from the first homework set on the seventh problem set, by the way, so you don't forget. Things add or subtract to the same unit. If that's a Pascal, then that's a Pascal too. Okay, what's important about that is, okay, this is a test, and now I've asked you to derive this, but somewhere else, I've given you the relationship like you know I'm going to, so that you have the answer, and I ask if it makes sense that this is equal to a Pascal. Okay, I can think of several answers. For one, what are the units of A? Joules per mole?
No.
No, joules, right? In the table, it may be joules per mole, but it's really joules, because it has to be extensive. Joules per mole is intensive, joules is extensive. Okay, joules over liters is what unit?
Pressure.
Right, pressure, the kilopascal specifically. Okay, our joules per meters cubed would be better, and that would be in units pascals. That makes sense. Here's another way to do this. So I've been manipulating you in lots of ways to get your money. Actually, I already got your money. And I spend them on kitties. And so here's another question I could ask. Okay, now, question 1 was derived. Question 2, what are the units? Question 3, does it make sense that DADV was equal to an intensive unit? Right, pascals is intensive versus meters cubed, which is extensive. Does it make sense that the ADV had an intensive answer?
Yes.
Why? Because, right, extensive divided by extensive ought to be intensive, and it is. Right, so if I'm doing this derivative, and instead I've got V, which all right, if I end up with volumes here, not only did I do the derivation wrong, okay, let's just get aside from that, how could I have known? I should have known that an extensive over an extensive should not give an extensive. Again, a way to know I've done the derivation wrong. All right, anyway, also very relevant to your homework. Obviously, the answer will be very, very similar. Might actually be the same, I don't quite recall. Okay, let's do some other ones. Let's go ahead and do DADP. Just for the hell of it, I'm just going to throw as many of these at you as I can. I do want you to get the underlying meaning, and I hope I've shown that. At the same time, when it comes to derivations, the more of them you do, the better off you are. It's just practice, right? Okay, so minus SDT, minus PDV. Okay, this is already a little bit more complicated. And now you have to look at the last, you have to look at the video that I gave last time, the PDT at constant S. Again, these are straight off my notes. It looks like I've unfortunately inverted what I'm trying to solve. PCP over VCV. Okay. All right, so this is fairly straightforward. It just has this, but this is inverted, but this is what I find on the internet. It has this, inverted of that, which I find on the internet. That's why I gave it to you, so let's figure out what that is. Okay, dTdP, so I have to flip this. There's a minus SV over CP. Okay, minus pressure divided by minus pressure makes that a plus. The pressures are gone. And then I've got VCV over CP. And let me simplify that. I've got a V over CP common. I'm going to simplify this for reasons I just said, so I can see if the thing makes sense. And what I've got left is CV from here minus S. Okay. There we go. And again, this is DADP at constant S, just for OCD purposes. There we go. There it is. Now, I can honestly tell you that when I was doing this derivation late last night, thinking of you, read my professors, I was looking at these two. I was looking at these two, and I was kind of freaked out because they really look different to me. And I remember thinking, well, okay, I'll just rip the pages up and I'll start over. I must have done something wrong. And I thought, maybe there's a way to double check this that's relevant to your homework, which there is. Let's do this. All right, let's write the ADP. Here, let me give myself a little bit more room. The ADP at constant S. Okay, relevant to your homework. If I add this guy in, this was an identity I gave in that first extra Friday hour. What's this? Do I need to use Euler's chain? Remember Euler's chain? Remember that? Do I need Euler's chain? Remember x, y at constant z, y, z at constant x, y, I forgot already. Do I need Euler's chain?
No.
No, because what's held constant is the same. Remember, Euler's chain ends up being equal to -1. It's a little complicated. It ends up being -1 because what's held constant keeps rotating, right? As you go term to term to term. This one is much easier. All right, so what can I do? Remember these, if everything's held constant, we're on the same playing field, and that means that the jugglers are all juggling the same balls. Now, if that's the case, A over B times B over C is A over
Delta V.
Right. Delta V, which is C. There we go. All right, so now, I have, what have I done? Okay, all right, I've got the ADP, which is this guy. I'm going to write this again, CV minus S. Okay, dP dV at constant S minus PCP over VCV. Okay, let's see here. The V's cancel, the CP's cancel, so I end up with minus P. Okay, that's gone, minus P over CV. Times CV minus S, which is carry through with the, actually I'm going to keep the P. And what I'm going to have is S over CV. And then I'm going to have, let's see, I need to keep a S over CV, but I need to keep a minus P. I need to keep -1, right? Oh. Okay, look at that. Same thing. Right, it works. Which is basically the answer to number 1 on your homework, essentially. To do something like that, but much, much, much easier. Okay. More examples. All right, so now this was the minus dsdt minus p minus pdv way. We all know that there's another way to do all this same jazz, which is to go the u minus ts route. Let's do that. So I'm going to do the same thing. Now remember that unfortunately the thing about PChem is that there's multiple ways to do the questions. It is impossible for me to herd you cats to do it one way, which would certainly make grading easier. God knows I try. So that complicates my grading, but what's good for you is that if there's multiple ways to do things, then you're not pigeonholed if you go the wrong direction on the first step. When there's only one way to do things, if you get it wrong on the first step, you're screwed. Here, every step is correct. It's just a matter of how many steps does it take you to get to the answer. Slightly to your benefit. Not hugely, but it helps, all right? So let's go. The dA is du minus ts minus tds minus sdt route. Okay, same thing, right? And we're doing adiabatic reversible, so I can do that. Okay, then let's do dA dv at constant s. Now, again, I know that I am adiabatic reversible, so the change in U is CV dt. dV, constant S, minus S, dt dV, constant S. This is, where am I at? TdV. What have I done? TdV, where is, sorry, I already forgot. CV dt minus PdV. So what am I doing? dt dV, constant S, which is because that's where that equation came from, is minus P over CV. Okay? Minus P minus S dt dV plus P over CV, which is P S over CV minus, oh, right, okay, same thing. Okay, again, I, on a test, would have had you started with this, because this is done in one step. Some of you would just completely ignore me, like you did last time, but that's okay. A lot of you got to the right answer using it the hard way. This guide is generally the hard way, but it will still lead to the same answer, which is great. You still get full credit. All you do is have me very tired and angry because it took me forever to grade your homework. So, anyway, but still though, I am glad that we have multiple ways to get to the same answer. Okay. All right, more. Let's just do more. Okay, so let's do change in temperature. And again, I'm going to stick with A, and then on homeworks I'll ask about G. Homeworks or tests. Okay, let's go the hard route. SDT minus PdV. And again, I'm just asking, at this point I'm just throwing up letters. Hopefully this has been relevant to your homework. I know it is because I wrote both. S, constant S. Now remember, this is why this kind of is sucky. This term doesn't magically disappear because a constant S, T is not constant. I know that adiabatic reversible temperature is changing. So what do I want to do with this? Oh, okay. The first term, again, I won't ask audience participation. You know that's 1 minus S minus P. Oh, I got dV dt at constant S, CV over P, minus plus, so that's CV minus S. There we go. And now remember, folks, that if this was the derivation on the homework, I'm likely to do dg, I'm sorry, homework is mostly done, right? So test, second test, possibly final, this would be dg dt. And I would ask, does it go up or down? And in this case, all right, I've already given enough hints, but in case you don't remember, absolute entropies, which I have bothered to measure of gases, because we're still in gas land, at least for now. Absolute entropies are about 100 to 300 joules per K per mole. And CVs, you already know, are 10 to 20 joules per K per mole. Sorry, per mole. We're doing 1 mole, right? So does this go up or down? If temperature goes up, does the ability to work go up or down? Down. Right. 10 minus 100, right? So it goes down. Okay, nice simple derivation. This would be too easy to be in the derivation section. It would be in the section right before that, the life of the universe and everything. The derivation section would have something at least taking 3 steps, not too easy. Not hard. And again, if you completely go down the wrong answer, it's still doable. All right, what else have I got? I got a couple more examples. Okay, let's do this. Let's do dAdV at constant S, dV dt. Again, this is relevant to your homework. I want to point out that this is dA dt at constant S, which I know the answer to. And I've already now, I know this is going to be really kind of cross-eyed. I'm just kind of saturation bombing you with derivations. I'm sorry, just, it is what it is. Okay, what have I got here? Okay, the ADV at constant S. Okay, I have it up there. I know, I hear one of you. Hold on 1 second. S over CV minus 1. Okay, there was a question? We're okay? All right. Anyway, I've done this up there. I know it's a lot. You're going to get kind of cross-eyed by all the derivations being thrown up everywhere. Just work with me as best you can and then watch the video later. dvdt, where is that?
Top right.
Oh, yeah, right, top right, yes, right. CV over, minus CV over P, okay. And what have I got? The P's cancel, and so I've got CV minus S. Right? Right, the P's are gone, so I've got minus CV times this plus CV minus, there. Oh, right. Same answer, totally makes sense. And in case, again, I don't like to do things ever where it's just a mathematical exercise. What I like is that it works. That's kind of cool. It's a good way to double check. It makes things easier. It gives you more ways to solve things. Remember that on tests and homework, when I ask you to solve things, and I'm going to give you the nicest hint possible, if you choose another route, thank you. It may make grading harder, but if you do it right, I don't care. I only care about answers, right? New modern world. Okay, so, and I hope that this isn't also just completely pointless. Remember that A is reversible work, volume is volume, so it tells me if I have a bigger machine, a bigger reversible adiabatic machine, does it do more work? Yeah, the answer is no. So don't do it, right? Don't build a bigger machine, it's a waste of time. Okay, so that's kind of nice. Okay, let's do more examples. God, what am I doing? Okay, I want to relate, let's do one that's kind of relevant to the homework. Homework number 1 again in a different way. And the reason I wrote out this example, and I'm actually almost done here, I think I've thrown enough at you, is that every time I do this class, I notice something new I never noticed before. And this one's kind of embarrassing. Notice that number 1 on the homework is all about understanding this little relationship. We're still at, we're at constant T. At constant temperature, the minus SDT term goes away. I'm not even going to write it down. And so that means that the change in G is VDP, but I also worked in class going to DH minus change in TS. If I went that route, I got to this relationship. Which, by the way, on the homework, when you do the gas expands, a gas contracts question, the isothermal gas expands, a gas contracts, and I ask you for all 12 variables, G and A are just reversible work. Be careful about the second question, which is irreversible. You still need to calculate the reversible work because that gives you G and A. That will be the thing that screws you up on the test. A question like that is obviously on the second test. So anyway, you know that. Okay, now what I got obsessed was I found this strange. I found this really odd, but every which way I worked it, it was true. And on your homework, you're going to work it. Again, a different way, using the methods I actually just did a minute ago. And so let's do this with A. If I do the exact same derivation with A, I'm pretty sure I'm going to get the exact same result. So instead of doing isothermal, I did isoentropic. So what I did was, let's do this. The A, and write down a result I already have. The AdB, the constant S, is P times S over CV minus P. And therefore, the A is P times S, sorry, this is me getting a little too fast, VB minus PDB. Sorry, I don't want to get confused about what I'm doing. Okay, but notice that dA is the change in U minus TdS, but I'm isoentropic, minus SDT. And so therefore they should be the same. Now again, I derived this under conditions of isoentropic And I did this under adiabatic reversible conditions, which are the same thing. So therefore, they're equal, and they are. Minus SDT. Got confused what I was doing. Okay, again, my point being is that I got really kind of fascinated with this little sucker here, how if the variable changes, that I can even change the variable and that they're different. So I tried to come up with the same thing. Again, if I did A at constant T, I'm pretty sure I come up with the same equation, so that's kind of boring. So I did isoentropy, and I came up with this relationship, how the T's and changes in T's and V's are related. And so what? Now, that's really all I got. I want to make sure whether it's correct. So what I'm going to do is go back to here. Let's go back here. And what I'm going to do is I'm going to substitute in dV. Using this guy, I've got dV is minus CV over P. Now what I'm really doing here is getting used to the fact that, again, these partial dVs are juggling balls. As long as I have the core condition of constant entropy correct, once I've got that nailed down, there's almost nothing I can't do. So what I'm going to do is plug in this guy for all my dVs, because everything's at constant entropy, and you're going to see whether I get to the same. Let me get this out of the way so you don't get confused. I want to see if I get to the same result. Okay, so I've got PS over CV. dV is C minus CV over P. Now I've got my dt minus P times minus CV over P dt. Let's see what that's equal to. Minus SDT plus the D's cancel plus CV dt. Oh, yeah, I got it right. I swear I wasn't looking at this. They're the same thing. Anyway, all right, just another simple derivation that I thought this was nutso. I confirmed it's correct, so will you. I derived a similar relationship, and again, I actually make sure that they're the same. And I don't know what else I get from that, but I know I got that, so let's go on. All right. Again, maybe some of these are just exercises in mathematics, but what I do get out of this one is to demonstrate, let's say I asked this on the test, it demonstrates that you do understand how you can manipulate relationships. And if you can manipulate relationships, you can manipulate people. And if you can manipulate people, you can get their money. And maybe that diamond will stay a diamond. Oh, you remember that. Okay, anyway. All right. I have 5 minutes. I've just got more derivations. Let's just do more derivations. Again, kind of related to the homework. Let's forget this constant entropy deal, which I hope you're not too cross-eyed. Remember that most of it is just algebra. That's really all it comes down to. Constant temperature is a little bit easier because your guts help you a little bit more in terms of what you should get. Okay, so let's do some constant temperature derivations, because you have one on your homework. Let's do dGdP, dGdP at constant T, minus SDT. Let's go ahead and get rid of that, plus VdP. dP, constant T, is V. And I'm done. Okay, this does not even belong in true and false. All right, if this type of derivation appears, it would appear in true and false. It's just too damn simple. And again, that's question 1. Question 2 is if pressure goes up, does G go up? Yes. Right. Okay. So there you go. Besides, right, I did this last session. All right, let's make it a little bit more interesting. All right, this is kind of trivial. Let's do it. Let's make it a little bit harder. SDT is that term is in common, so let's get rid of it. dP, dV, AP, constant T. I notice that some of you are still struggling with this. You cannot get this wrong. nRT over P, dP. at constant t, which doesn't matter, and this is one of those times that what's held constant doesn't matter. This is c over x, or c to the x minus 1, which is minus c over x squared, which is p, and that's volume. Okay, so it's still volume. All right, so that makes sense. Now, okay, now that's worthy of an actual derivation on the test because it's not too trivial. Let's do the same thing. Let me toss this up here. Okay, let's do a derivation that's worthy of the derivation section, which is let's put in a real gas equation, and then we'll analyze the real gas equation, which would actually come in an earlier question on the test, the way I designed the test. Anyway, here, you'll see what I mean in a second. Let's do for a real gas. Now, I'm going to use this. I've been doing this a lot lately just because it's different than what I've done before, to be perfectly blunt, and it's relatively easy. I have this modified virial equation. Okay, without the c term, without the c, n over v squared. Okay, if we plug this guy in, let's see, I've got dA dP is minus p. Now, remember, on the very first day, the very first homework, sorry, you had to do dV dP, something like that. And you had to do van der Waals or Berthelot, I forgot. The point was, there was no good way to do it, unless you had some trick, which in the homework's case was to use the Euler chain. In this case, I'm going to flip it. Right? Because it's really easy for me to write P as a function of V. It is actually impossible for me to write V as a function of P, because I can't get the V's on one side. Okay, and this is minus, tell you what, let's do dV dP. And I'm not going to write the constant t because it doesn't matter. The name of the game is to write the function in a way that will make this easy. And to do that, I'm going to factor. So this is something that some of you this is what cost you some points, and it really shouldn't have. Because it's really simple, RT over PV squared. Okay, this is the derivative of x of c to the x minus 1 plus b c to the x minus 2. That's what this is. This is very, very easy. Minus nRT over v squared minus 2b n squared RT over pv to the 3. What I'm going to do is factor this for reasons that will be quite clear in a second. I'm going to get out this minus. I'm going to get out a minus 1 over v, and that's going to make the rest of this positive. I'm going to have an nRT over v, and that leaves a, just so it's a little bit more clear what I'm doing, 1 plus 2b n over v. Okay, now let's plug this into here. Okay, I'm going to do a lot of algebra in my head, and I do that for convenience and also to make you work a little harder. Minus p over 1 over minus v is pv. Okay, I've just taken out this term, and then what I've got left on the bottom is nRT over v, 1 plus b n over v. 2bn over v. Okay, and that's sorry, OCD, and that's the answer. Now the issues are here that I want to make sure the units are right, and let's see, it better be units of volume. It looks like I got volume times pressure. So I bet this pressure needs to get wiped out here. Note that this, you see, if I divide this by V, I almost have pressure. You see how close it is? See how close this is to pressure? In which case I return the perfect gas law, V. But it's not the perfect gas law, nor is this pressure, right? So you see how a real gas is different than a perfect gas. let's do this a little bit further. Now, B's tend to be negative. For most gases, B's are negative. So is this more or less than pressure?
Less.
Right, now remember you have to compare it to this. Right, this thing drives the pressure down, but now it drives it down more, less is correct. Okay, so this is P over slightly less than P, meaning that this is slightly greater than B. Right? So in other words, a real gas has an increase with A with pressure greater than that of a perfect gas. In other words, a real machine at higher pressure does more work out than a perfect gas machine. It's a better machine. So real gases are better machines. That's what I've learned. Real